So thanks all for coming today. I wanted to share with you guys some of the different stuff that we've done and hopefully get some of you excited to do some of it down here. If you guys do make some of these things down here, definitely send me movies because I love seeing what other people do. So as Lex said, a lot of my stuff is really in trying to look at how to change how we learn, how do we get students to learn really, especially around the engineering world, and do a lot of work with your tax dollars, National Science Foundation, so thanks for that, and as well as National Instruments and Lego. So I thought I'd start with just a little bit of history of Lego. Does anybody know what company owns Lego? Any guesses? Lego. That's right. Nope. Lego is a privately owned company. This guy here, Keller, owns Lego. So if you guys need pieces that you don't have, whoa, that was cool. He's the one you want to talk to. So it was founded by his grandfather in Denmark. Originally, his grandfather was a carpenter, and during World War I, he found that the one way he could make money was to actually make children's toys. That was the one luxury item that people would actually use money on. So he started making wooden toys. He actually became a distributor for small plastic stackable bricks that were out of Britain. They didn't work very well, so he started to improve them. Gottfried, his son, then took over the company and really improved them. The factory burnt down. When they rebuilt it solely to do plastic. They put everything into the plastic world, and Lego started to take off. And it was really Gottfried that turned it into a large international company. How many people here have been to Legoland? It's a great place. I highly recommend it. It's one of the few places where I've actually taken my kids who are older and actually had to tell them, hurry up, we got to go. I want to go on some rides. Because they have these things called mini-lands where you can walk around and they've built absolutely everything out of Lego. It's really cool. So anyway, Gottfried had a few kids. Kelt was one of them. Kelt now runs the company. He has 2 kids. They are probably going to run the company when Kelt decides to step down. He actually has a full-time CEO, so he sits back and enjoys life and discusses the finer points. So about 15 years ago, a professor at MIT, Seymour Papert, became the first and only, no, that's not true, the first holder of the Lego professorship at MIT, something I've always been very jealous of. Really cool to say you're the Lego professor. Really cool. So Seymour Papert, for those of you who know something about educational theory, came up with a theory that people need to construct their knowledge to truly understand it. And he convinced Lego that they had a great tool for such construction. And in particular, he was interested in the merger of the physical world and the virtual world. So they came out with the Control Lab interface, which is this little puppy right here, which is really cool. For $200, you could actually turn motors on and off. You could read sensors, and that was pretty exciting. And that's where we started to get involved. So it actually, as Lex said, we actually started to develop RoboLab, which was the software that was used in the schools for the RCX, which followed this. And then the NXT and now EV3 have moved on to new software. So we are, our stuff is old news. But it's kind of cool. So what happened is they came out with this thing, and I was a young professor. I didn't have any gray hair. I didn't wear glasses. It was a great time in my life. And I wanted to buy something for my students at Tufts that would actually allow them to take data in their own room. And this was $200, and everything else was about $2,000. So I said, this is great. So I went to Lego, and I said, look, is there any way you can tell me how to talk to this thing? I want the protocol that you send across the RS-232 connector. And they said, yeah, right, that's confidential. So being an arrogant type of professor, most professors are, I reverse engineered it, and a student and I reverse engineered it. We went back to them a little bit later and said, look, this is what we were talking about. This is what we could do with LabVIEW and your Lego tools. And so we came out with that software, which we called Lego Engineer. And you could do stuff like open up, close a greenhouse, and all that. And you know, I'm very proud of what I've done. I show it to Lego, and the guy goes, that's really cool. And I'm thinking, yeah, this is cool. He likes my software. He goes, you're doing it on a Mac. I said, well, yeah, of course. Are there other computers? I mean, what other operating system would you use? And he goes, well, we have a problem, actually. We're going to be coming out with a new product that we can't tell you about, but we need a Mac version. And would you be interested in working with us to develop something for those schools in the US only that actually use Macs? And I said, sure, you know, free Legos, why not? And when I'm talking free Legos, I mean you get the catalog and you see there's a Batman set and you say, excellent, we want them all. I mean, this is the time. This is like great stuff. So, so I signed my life away, my first 2 kids, and then we start developing RoboLab. And they give us the RCX, which is the precursor to these, and we start building stuff with it. And what I want to do is to start out is show you some of the things that people built. So we'll start with what can you actually build with a control lab interface. So this was built by a student who decided, really, we want to get into the world of the Terminator, right, where you have Legos building Legos. So what you have here is a camera that faces down. It identifies where the Lego piece is. It identifies its orientation. It sends the grappling hook, or whatever you want to call it, the grasping arm over, goes down, picks up the piece, moves it back, and puts it on the board in the back, and then goes and grabs the next one and does it again. Something that any 3-year-old can do. This took a graduate student about 2 months to make it work. So we haven't quite made a Lego 3-year-old yet, but we're getting there. So then we moved into the RCX, and the RCX the big difference is the RCX was not attached to the computer. It was not tethered, so it was free to move. And we started first in getting people just involved in making it go forward and backward, and then we started saying, well, you can run science experiments with it. So how do you actually take science measurements and so on? And then we did image processing with it, and we really went to town. And I'll show you some of the things that we actually did in schools right down the street. So this was Riverside School in 2002, where we asked them to build animals with the Lego pieces. And so you can see that that was Snakey, obviously a snake, as you can tell.
Very big one, too.
Yeah. This was a dog that when you patted on its head, it would stop for a while, because it kind of liked being patted, and then we'd continue on. So you can see it has a touch sensor on the top. That's what patting on the head is. This was a tiger, in case you couldn't recognize it. The key thing about the tiger is that it goes fast. Everything else is unimportant. Obviously, a hammerhead shark. And then this last one, no one really knew what it was, but it's a genetic anomaly of some type, but they were very proud of the legs. Like, super cool.
I think it was the Kingdom of Atlantis on wheels.
Above water, too, which hasn't happened in decades. So I ran exactly the same problem to a bunch of Princeton students to see how they would compare to Riverside 3rd grade students. They did OK. Exactly the same problem, same set, build an animal that moves forward. And this is their final inventions, all rushing down to kill you. There's the gorilla that would stop and play Darth Vader music to try and intimidate you. There's an elephant, a dragon that would actually breathe fire. That, I think it was an owl? No, I don't remember what that was. Something very dangerous, though.
Other bee?
Not something I'd want to meet in a dark alley. And I figured I'd show you Gaston. Gaston was made by a couple of high school students in Luxembourg. He determines whether or not he likes you by the temperature of your hand. So you shake hands with a temperature sensor, and that determines whether or not he smiles. He also has 2 ears and can localize the sound of your voice. So figure out where your voice is coming from, and he'll follow you around the room. So it's pretty impressive to get high schoolers to actually learn something about cross-correlation techniques to localize the source of sound, just so that they can make Gaston follow you around the room, is what I would call good stuff. I agree. This was actually out of one of my classes. One of the biggest issues in robotics is figuring out how to make the robot go where you want. And these guys figured out how to make it follow a line, but follow a line really fast, which it was an all-male group, so you need to go fast. Does anybody know what it's actually following?
The black.
Yeah, but what does it say?
The border. Yeah.
Tufts, very good. Who said that? Outstanding. You coming in 10 years? I'd highly recommend it. We have a great Frisbee team. This is actually a bunch of middle school kids in Switzerland. They decided there's no reason that they should cook their own hamburgers, but in fact it would be much better if the Legos cooked the hamburgers for them. So they went to one of their teachers and said, we really would like to make a thing that cooks hamburgers. So the teacher actually didn't have any Legos, didn't have any background in this, but she figured this was a cool idea. You need a Lego hamburger cooker. So she got borrowed stuff, got it to happen, made it happen, and the kids developed this and filmed this, made this, designed this, and were so into this that she now does it every year. And they've made cake makers, hot chocolate makers, you name it. They have the automated kitchen of everyone's dream. The new cool thing about this is you can actually eat what you make at the end, although I don't understand how anybody could eat something with pickles in it. How many people here like pickles? Oh, that's depressing, man.
I do have a sister who won't eat pickles.
Ah, there we go. She's wise beyond belief. So then came out the NXT. This was the NXT is this guy right here. A little bit bigger, a little bit less colorful, not nearly as yellow, but a little bit more powerful and has a bigger screen. And so we ended up helping in the development of some of that language as well, mainly the language for the high school area. But we also ended up doing some pretty silly things with it, like driving to work with a Lego car.
That could take a while.
Yes, it definitely did. It was not the most efficient method. We actually flew an NXT with the only Lego quadcopter that I know of.
Looks like it might be kind of
No, don't hit the water.
It flew once,
And then,
as you can see, and then bounced.
well, at least it didn't go in the water.
That's right. It's another one, another class. They built all sorts of assistive devices with Lego. So of course, the first thing that you would think of if you need to assist people would be a thing that solves the Rubik's Cube for you. So they have a Rubik's Cube solver. They made a slightly easier Rubik's Cube of a 2x2x2. The next one is actually the most complicated one. This tracks your pupils. That's a camera that's on his hat. It tracks your pupils and drives your wheelchair according to where your pupils are going. So if you want to turn right, you move your pupils to the right. If you want to turn left, you move your pupils to the left. There's your wheelchair. If you have to do it, though, with one eye closed. If you have both eyes open, it ignores you. So if someone calls your name and you look over, your wheelchair doesn't go flying off the street. You obviously need to work on your reflexes, so you have something that passes the ball with you. A lot of engineers don't have friends, so we have robots that throw the ball. This one was pretty neat. This was actually a system for blind people to see pictures. So as the robot drives over the picture, it moves up or down, depending on how white it is or how black it is, and so they can physically feel what the picture looks like and try to identify what's going on. This was out of the University of Zurich. They had a high school student that they challenged. They gave the high school student 60 pieces, and they said, how many different ways can you move forward without using wheels? And this is what the high school student came up with. The neat thing about this is in all of these robot cases, the programming is the same, the materials are the same, but the behavior of the robot is completely different depending on how you put the pieces together. You can see some of them are fast. Some not so much. This one works hard, but doesn't quite get it. This one's my favorite. He tries so hard. It just doesn't work. And then in this summer, Lego is coming out with a new one to replace the NXT called the EV3. That's this guy right here. He looks a lot like the NXT, but it's far more powerful. For those of you that love this kind of stuff like I do, this is a full Linux-based machine inside here. It's got its own SD card. You can reboot it with any version of Linux you want. You can turn it into a web server. You can use web services to control your robot. You've got 4 motor outputs. You've got 4 sensor inputs. The inputs are I²C, so you can attach any sensor you can imagine. This guy actually has over 50 different sensors. It can measure your heart rate. It can measure pretty much anything you can imagine. This guy is going to be orders of magnitude more. The software for it's going to be a little bit different. I figured I could show it to you quickly. There's basically what happens is you have different controls that you can move up. So if we want this thing to drive forward, we can say we want our car to drive forward. And because I still believe in kindergarten, we're going to drive forward at max speed. And we can hit run. But you didn't know forward was this way, did you? And you can actually see it run. If you watch the screen, it'll show you it running. So
Which screen
look right here, and it can show you which one it's running by which thing is. You see how you can see the lines moving? That tells you what part of your code is running. So this also has a full data logging area in it. You can graph stuff and make musical instruments and whatever else you want to do. So that's coming out in this fall, and hopefully we'll be going into 1 or 2 schools so that kids can build stuff. So what I want to do for the second half of the talk, though, is talk a little bit about why we're doing this, what we're trying to do with it, why you guys all should be telling your teachers you want to do engineering in your classroom. You don't have to do Lego, but you want engineering. And this is something that's come out of the center. At Tufts, we have a Center for Engineering Education and Outreach. It's almost 20 years old at this point. And really, our main goal is to try and get kids to learn how to stop following directions and start engineering, start thinking on their own, and figuring out how to validate their own thinking. So if you think about it, the way a friend of mine, Yanis Miolos, he's the head of the Museum of Science in Boston, the way he puts it is very, very powerful, I think. He said, take a minute and look around and remove everything you see that is made or designed by an engineer. What do you have? Well, you weren't designed by an engineer, so you'd still be there, but your clothes wouldn't be there. That's a little embarrassing. The room wouldn't be there. The seats wouldn't be there. So now, how much of your time in your first 12 years of education have you spent learning engineering and how engineering works?
Not so much.
Not so much. Why is that? We spend more time studying volcanoes than we do studying engineering. How many people here have been in a volcano? Actually, I have. They're very cool. I highly recommend going. How many people here have been inside a car? Wow, a couple of you haven't? I'm impressed. So how can we get more of the engineering in the schools is what we're really looking for. The center has about 100 people that work for it. We split it down the middle between education research, so trying to understand how you think, how do you learn stuff, how does the brain actually take in information, retain information, access information. And right next to them are people that are doing their PhD in engineering. How do we design new tools to take advantage of this knowledge we have of how your brain works? We then work with a number of different companies, including Lego, to take some of these ideas out into the classroom. And then we have a large outreach arm that works with teachers all around the world that then closes the loop. It brings back the information from the classrooms to sort of inform us how to move forward. It's a whole lot of fun. That's why I'd recommend coming to Tufts. So what do we want to see? Right now, I would contend that in a large part, we're really not teaching our kids science. And we're not teaching our kids engineering. What we are teaching our kids is how other people have regarded the world around them. So I see science really as trying to make sense of the world around you. And we don't really teach that. We teach you how others have made sense of the world around you. And as a result of that, we get a lot of kids just memorizing things instead of actually trying to think deeply about the problem. We don't get kids having opinions, right? Think back to when you were in 9th grade English, or think forward when you will be in 9th grade English, right? English was pretty cool. You read the book, you had an opinion. You thought so-and-so was a jerk for these 5 reasons, right? You wrote an essay about it, you argued it in class. You had your opinion and you could substantiate your opinion with evidence. You then went across the hall to chemistry class. How many opinions were you allowed to have in chemistry class? 0, right? You'd say, I have an idea. And the teacher said, no, that's wrong. So all of a sudden, you're not really that interested anymore. Where do you actually start to get having opinions in science? In graduate school. And it's really fun, let me tell you. So why can't we get some of that a little bit earlier on? And it turns out engineering is a great way to do that. Because we can really get kids to think and design and develop their own ideas. One of the critical things about engineering, and I think we can do this in science and math, but it's a little bit harder in math, is to really have people come up with different solutions to the same problem. So what is it that I mean by doing engineering in the classroom? What are the things I'm looking for? And you can be looking, everybody's got their own favorite design process. Mine's very simple. It's 3 things. It's teaching people how to frame a problem. What is the thing they want to solve? Both in college and in kindergarten, we have a lot of kids that solve problems long before they figured out what it is they want to solve. And as a result, don't really solve the problem they were supposed to be solving. Once you've figured out what goal you want to get to, what is it that you want to solve, and in this case, obviously, it's building a sculpture of yourself, because that's what anybody really wants, you plan a path to get to that goal. So how are you going to do it? And as you start going down that path, you realize it's not going to work. You're going to fail. And you do it again and again. So an integral part of engineering is failing. We fail all the time. It's also an integral part of soccer, right? How many people kicked a soccer goal the first time they kicked the ball? OK, so we have one that's brilliant. But other than that, you had to go again and again and again until you got the skills down to do it. Well, it's the same in engineering. And I would argue it's actually the same in science. So what does that mean? It means that I want problems. What I want in my kids are I want them to be innovative. I want them to be creative. I want them to work together in teams. I want them to solve problems. And to do that, I need to give them messy problems, not problems that have a nice, clean answer. There is no answer key in engineering. There really shouldn't be an answer key in anything. Answer keys are bad, right? I want problems where nobody knows the answer, and you have to figure out how you're sure your answer is correct. So give them messy problems. Teach them how to fail again and again and again. And really, one of the ways that I measure success in my classroom is the diversity of solutions across the class. Not is everybody getting the same answer, but how different are all the answers. So Lego does a great example of this. They give you 6 bricks, and they ask you to build a duck. It's 6 bricks. I mean, how many different ways can you put 6 bricks together? You'd expect everybody's duck to look the same, right? This takes 2 minutes. And inevitably, everybody's duck looks completely different. It turns out there's millions of ways you can stick 6 bricks together. So this is exactly the type of thing that we try and get in the classrooms. How can we give problems where, just like you saw with the walkers, same problem, but tons of different solutions. Why? Because now all of a sudden you realize you can learn just as much from your friends as you can from your teacher. So the classroom goes from having 1 teacher to 20 teachers. So what are the ultimate teaching goals? So in my case, the things that I found that what I really want to teach, what I want my kids to know when they leave my class, are first and foremost how to be curious. So really how to ask questions. Your average 5-year-old, their favorite word is why. Somehow when people come to me later on, except for Tyler, when people come to me and ask me about my PhD thesis, and I start to tell them about particle-laden turbulence, nobody asks why. They run, which is too bad because it's really cool stuff. If you want, I've got a whole other lecture on that. We can talk about that. But so once you've taught them curiosity, then the second thing is to how to find answers on your own. And that can be as simple as going to the web, or as difficult as building up your own experiments that you're going to try and find out your answers. And then, of course, how do you reflect to see whether or not the answer you found is correct? Because believe me, I can find any answer on the web. I can find that the Earth is flat, that Harry Potter is the devil, you name it, I can find it. So how do you validate the answers that you find? And then lastly, once you've figured out the answer, how do you have the self-confidence to transfer that knowledge, that information into new areas? Because it's that transfer where we really start getting innovation to happen. So these are the things that I'm trying to teach. You'll notice it doesn't seem to be too unique to engineering. English teachers see this and they say, well, that's exactly what we're trying to teach, which is great. So how can you teach it? Well, so what I want to do is take some of the research that we've been doing in education and package it in to show you some movies, video clips. So the first thing that all of the research shows is that there is no one right way to teach anything. Right? It makes sense. There is no one food that everybody thinks is awesome. I mean, a lot of people like tomatoes, but I think tomatoes are gross. Right? So how many other people think tomatoes are gross? All right. It's actually a higher percentage than I thought. So what we need to do is we need to start realizing that there is no one right way to teach anything. The way you learn the material is not necessarily the way your students are going to learn the material. So you need to present things in multiple ways. The other thing is that we are starting to get knowledgeable about how your brain actually works. And it's about time that we actually start doing education based on science as opposed to education based on hunches. Right? Typically, we have a hunch this is going to work, so we're going to try it out. There's a lot of science out there in actually understanding how the brain works and how the brain learns, and we should be taking advantage of it. So one of the ways you can teach is like I'm doing right now. You can teach by talking. And there are people that give good lectures. There are people that give bad lectures. It's definitely a way to get information across. Since it's so ubiquitous, I'm not going to spend a lot of time on that. Another one you can do is teaching by investigating. So I can give you tools that will get you to want to learn. So for instance, this is an IR camera that we put in the hand of a 5-year-old. Happened to be a 5-year-old that had a chicken. So she started wandering around and she was taking pictures of things around her. So the chicken, she takes the pictures of the chicken and she starts to wonder why the chicken's head is red and its feathers are green and then there's even sections of blue. And what do those temperatures, what do those colors mean? And why is it different on the chicken from the human? And then we start to talk a little bit more about, well, let's look at an object that's changing in time so she can actually see how the coffee cup cools or heats up in this case. And my favorite is you can actually look at thermal shadows. So this is a picture of a window. To you, it just looks like a window. But through the IR camera, you can see that somebody had touched the window a couple minutes ago and left and heated the window up slightly. And so you can see it in the camera.
That's so cool.
It is cool. You know what's really cool is I can actually take that same camera. I can look at a couch. I can tell you how many people sat on that couch and how long ago they sat on the couch. I can look at a parking lot and I can tell you where cars used to be parked. I actually can look at the wall and tell you the path the sun has taken as the sun rays come through the window and hit, not this room, but in any room that has glass to the outside, sun rays come into the wall and heat up the wall. So all of a sudden you get kids asking really good questions. When we put this in front of some of my college students, one of them dropped down and started doing push-ups to see if he could see the increase in temperature of his muscles, which was pretty entertaining. He couldn't, but. So the administrator for the center decided one day she wanted to know what her plants did overnight. So she set up a camera to take a picture of it every minute. You can see the clock running in the background. And she came back and she played this. And we were all amazed. Do you know the average velocity of a plant leaf? I do. It's pretty cool. It's gotten me far in impressing my wife. But so anyway, when she came back in the morning and showed this to us, everybody was crowding around trying to figure out, is this true for all plants? Is this because where the plant was? Can we put the plant in different areas? And so all of a sudden we had a great science experiment going on where we were testing different plants in different areas to see how much they moved. One of the great things here is nobody knew the right answer. There is no right answer, right?
Right.
But we're trying to just figure out what's going on. And it's that investigation that we're trying to do. Another program that we've been working on is with kids with autism and how they can learn social skills through engineering. So in one case, we actually ran a summer program and then a program all last year where kids worked together to build different Lego contraptions and through the building had to interact with each other to actually complete their build. And we found that the kids got really excited about what they built, and because they were so excited about what they built, they would actually work on their social skills with each other. Another one that we've been messing with is the Now robot. This is a walking robot that you can program to walk around and talk to you. So one of my students who was working on the summer program and came up with this idea of what happens if we turn this walking robot into a storytelling robot. So what happens if you can make this robot tell your story? And so we built this website where you can actually type in whatever you want the robot to say, and you can tell the robot what gestures to make. So you maybe use your hands and go like this, or like this, or like this. And what we're interested in, and we haven't done the experiment yet, is kids with autism, what nonverbal cues will they have their robot do? Because one of the problems kids with autism have is picking up nonverbal cues when they're talking. They don't notice that you're mad or sad or frustrated. And it's picking up those nonverbal cues is one of the difficulties that they haven't have to learn. So what nonverbal cues will they put with this robot? So stay tuned. I'll tell you next year. You can also teach by listening. So listening to the models that the kids have in their head. And this is easy to do if I have a class of 10 kids. It's very difficult to do if I have a class of 200 kids. So how do I get a lot of kids to listen to each other? And one of the ways you can do that, again, we use stop-action movies for just about everything we do. So you can make a stop-action movie that explains your idea of temperature. And so if two kids are working together on this, the first thing they do is they argue, right? Because they've got to now agree on what they're going to make their movie about. Then the next thing they do is they've got this movie, so they share it with their friends. Now their friends and they start arguing, because now their friends saying, well, that's not really what I understood temperature to be. And then they get really proud of this thing, and they start sharing it with their uncles and their aunts and their cousins. It's amazing. We've had people share their stop-action movies with all sorts of people. And because of that, they keep arguing, keep discussing, keep thinking about what temperature means. Another one that we've been playing around with is having kids actually read books and try and build stuff within books. So in this case, how many people here have read the Mixed Up Files of Mrs. Baisley Frankenweiler? All right, not bad. You should have. So it's a story about two kids that ran away from home and lived in a museum. And so in one part, they decide, the kids try and find engineering solutions to some of the problems they run into. In one place, they want to be able to see over all of the people in the museum. So these two kids decided to build a periscope. And in building a periscope, they started to come up with all sorts of engineering constraints or engineering issues that they'll have to address as a result of the book itself. So the book provides a great context to give you a rich problem. So they wanted to make the periscope out of wood, but how would you get wood in the middle of the museum? Right? Would they have access to that? One of the kids in the book doesn't like spending money, so would they actually have spent money for the book? So what we find is not only are the kids getting a chance to engineer, but they're thinking more critically about what they've read as well. And so actually the teacher was a lot happier about the reading side, and we, of course, were excited about the engineering side. But my favorite way to teach is by building. So you can actually get kids to build their understanding of things. And I wanted to show you a couple of examples of how this would work. So one way we can do it is, this is one we've done a lot with younger kids. I can ask you to build a little Lego robot. So we'll build a car. Let's see. So give the car some wheels. And I want this car to drive, let's say, from California to Chicago. Okay, so we have a map of the US on the floor. Actually, we're going to go through the Midwest. Have you ever been through the Midwest? It's great. It's flat. Nothing changes for a long time.
Except the Rocky Mountains.
I grew up in the Midwest, yeah. That's true. Once you hit the Rockies, it all changes, especially if you're on a bike. So we can program our car. We can program our car to go for 1 second, or in this case, 1.5 seconds. So let's download a program. And it will download it into here. And we can run it. And it goes for 1 second, or 1.5 seconds in this case. Pretty cool, huh? You want to see that again? A robot that drives. What will they think of next, I tell you. So what's interesting is 1 second or 1.5 seconds doesn't go far enough. So you have to go a little bit further. So you try 2 seconds. Well, 2 seconds is too far. So we need something between 1 and 2. So all of a sudden, kids are starting to learn about fractions. In fact, one of the most interesting discussions I heard was kids getting really frustrated that a car that went for 1.5 seconds went the same distance as a car that went for 1.50 seconds. Right? Why would a car that's going for 1.5 seconds go for the same distance as 1.50 seconds? So that gets now that you're starting to understand some of the issues the kids are having and what the kids' thinking is on the stuff. You can also do the same problem for kids in college. So I do this in my controls course. I ask kids to actually, they do the full simulation in this case. They actually model the car. And we figure out, again, can we make the car go a specific distance? In this case, a specific number of degrees of the wheel. So you can see that. We can hit run. And you can see it's a beautiful system. Clients will be so excited. So you can change your parameters, and you can see it overshoot and all of that. Should we see it overshoot? It's kind of fun. There, you got a little bit of overshoot. So my students have to do all the modeling of this and see if they can actually make it balance on 2 wheels and other such fun things like that. I thought I'd show you the most complicated Lego robot I've ever been involved with building. This is the only robot I know of that's been driven by a fruit fly. So we took a fruit fly and we glued it to the end of a 3-dimensional force sensor. Luckily, there's no fruit fly rights activists, so it wasn't a problem. Now, it's a little known fact that fruit flies fly based on optical input. So if they see stuff coming at them at the same speed, they think they're going forward. If it's going faster in one eye, they think they're turning. Right? So we can give them an optical input, and then we can pick up their wing beat. So the wing beat controls the speed of the motors, and some proximity sensors will control what the fly sees. And in this way, we can program the fly to either drive the car to avoid obstacles or to drive into obstacles. So this is Chauncey. He's actually the graduate student who really did the work. his real PhD thesis was modeling fruit fly intelligence using modern control theory, but we decided we had to make a Lego car that would drive into objects. So this is a Lego car that is driven by a fruit fly. It only costs about $10,000 if you want to make one yourself. You can see it's not that repeatable. Fruit flies don't make very good chauffeurs. If you take one thing away from this talk, that's what you should remember. But they are a whole lot of fun, especially when you shoot them after little kids.
She walks away. But no, she comes back.
So I wanted to end with a couple different things that we've been trying to move robotics into. One of them is to try and combine the robotics and musical instruments. So here is a musical instrument that you can build that actually plays different notes depending on where you spin the wheels. In fact, we have a little adapter that we can take the robot and connect it directly up to GarageBand so that whatever you do in front of your robot will actually play different notes on GarageBand. Now is the time for me to give a shameless plug for all you in Princeton to take Rebecca's class so you can actually make this kind of stuff because it's very cool. Or you can do stuff like have it do the Etchasketch for you because you never really want to do the Etchasketch yourself. So this was some software that was developed by an undergraduate. It takes a picture of it takes any picture you give it, it converts it into lines, and then it draws a line out on the Etchasketch. So can anybody tell me what it's drawing?
Zigzags?
Oh, but what is it? Yeah, good guess. Ah, very good. Who said that? Abraham Lincoln, correct. See, he's facing this way. That's his hat. There's his chin. There's his nose. Yeah. Everybody needs one of these. So really what I want to leave you guys with is really we need to rethink how we do education at all levels, from actually kindergarten's great, but from first grade all the way through college, of really how can we get kids to think on their own, to come up with their own ideas, to validate their own ideas, to make their own decisions. And I think the sort of three central things I'd like to leave you with are, first, the belief that kids at any age are budding engineers, whether it's 3 years old or 30 years old. Right? Everybody loves to create stuff, and we should be taking advantage of that. They're willing to fail again and again and again if they can create something. We just need to give them that opportunity to do it. The second is that teachers are incredibly important. They're an incredibly important part of the equation. So this idea of trying to do all of your education online, of doing it through watching YouTube movies or however else you want to learn is a problem. And the reason is because teachers understand something about the backgrounds and the cultures of each of their students, and therefore can change the curriculum accordingly. And the key, though, is to really work with teachers on listening instead of telling, and listening to the kids and the kids' thinking. For those of you who have had teenagers, it's pretty obvious. If you tell a teenager to do something, they probably won't listen to you. It's much more listening to the teenager's idea of why they think they should be doing, allowed to drink, drive, or whatever it is. And then you go on from there. So, and then the last one is the classroom makes a huge difference. A classroom like this will usually lead to lecture like we're doing. A classroom that has tables and Lego pieces and 3D printers and laser cutters will be one where kids are up, moving around, using their hands to learn. And we need a mixture of both. So the last thing I wanted to show you is something that my boys made along with the guy who works at the center, just to show you that if you have the right tools, you can violate every law of physics out there. So this was, again, taking a stop-action movie. You take a picture every couple minutes. The idea here is you move a little bit, then take another picture, then move a little bit. And you can see all of a sudden you can acquire skills you never knew you had. So anyway, so thank you very much. I'd be happy to answer any questions you guys have. Thanks. So questions, ideas, goals. No questions? Yeah, John.
Very technical question. The next generation of this, what do you call it, RxD?
This one's the EV3 is the new one.
Okay. Is it an ARM-based architecture? instead of running Linux, it's like a...
It's a good question. I think they actually have 2 of them in there. One of them is a TI chip. It's the same as in the BeagleBone, essentially.
Okay, that is ARM-based.
And then they have a second, I think it's a second, I should know this, a second ARM 7, ARM 9 that's doing the PWM and so on. I don't remember.
Okay. So it's similar to our smartphones.
Yes, basically, with a much worse display. No touch. Yeah.
Curious about the new software for the EV3.
Uh-huh.
So I've got a Girl Scout robotics team, and they've got some experience with the nets.
Uh-huh.
How much difficulty will they have moving over to the? They look much different on the street.
That's the $1 million question. Lego is banking on the fact, it actually is more than a $1 million question. Lego is banking on the fact that this will be a lot easier. So there are a number of fundamental changes to the software. One is it's easier to read over the shoulder of the kid. So instead of having to click on each icon and see how they set it up, you can see all the settings on the actual icon. The second is that the instructions are actually embedded in the software. So you can read instructions, you can make your own instructions, you can take pictures of what you've done, all of that in the software. So I'm hoping it's better.
In your experience, what's the best way to get teachers to listen more and tell less?
So the issue is a good question. And the best way I've found is to show teachers video of what kids are actually, the thinking kids are actually capable of doing if given the chance. But the issue is teachers have all of this stuff that they need to cover by whatever, June 5th, right, for the standardized exam. And if I'm sitting here and listening to all you, I'm not going to make all this stuff. So it's spending a lot of times with teachers figuring out how to balance the instruction and the listening.
Yeah, do you think that
Tufts is a great place? Yeah.
do you think that adding like really it seems like the new RCX or whatever it's called is it's focusing on adding more and more gadgets. So do you think that that is going to defocus the learning and education aspect?
There is a lot of discussion that goes into that. As the processor becomes smarter and smarter, it screws up less, and if it screws up less, that means there's less learning going on. So it's this balance of, so yes, I think they are missing the mark in some cases. I think in some cases it's a lot better because it's a lot easier to debug and so on.
Yeah.
Yeah.
How did you get the EV3 if it's not out until the fall?
I have connections. I have this friend.
Considering you made the first.
Well, we didn't make it. We helped develop the software. And in this case, we're helping test a bunch of stuff on it. We've helped with some of the software development too. All right. Well, thank you very much. If you guys want to come down and play with them, you're more than welcome to.